Hi again, it's Miss Berry. Today we are going over section 5.2, which is called the binomial distribution. Sorry if you see my lights being crazy. I think maybe my office is haunted, but that's a totally different story. So I'm going to go ahead and share my screen. Oh, as you can tell, I'm doing screen recording again. So that means we're using the calculator. So get your calculator out and get your notes ready if you're going off with the guided notes. Um, and we'll get started. Okay, so here we have the binomial distribution. We're going to be looking at two specific types of um, discrete probability distributions. That's what the binomial distribution is. It's just a specific type of problem that we see come up pretty frequently. That is a discrete probability distribution. So binomial distribution, these are going to be problems that have these certain properties, but let's just keep in mind that they are a type of discrete probability distribution, which means that they are only allowed to take on certain values. So remember, we're just looking at discrete random variables in this chapter. Okay, so we're going to be looking at two different distributions, the binomial distribution, and then we'll look at the Poisson distribution. And once we have looked at both of them, I'm going to make a really short video where I give you some examples of here's what the problem would look like if it was framed as a binomial problem, and here's what the problem would look like if it was framed as a Poisson problem. So whenever we first go over these, you're going to think like, oh my gosh, these sound so similar. But I think once I make that little video, it'll really help you see the nuances of each distribution. All right, so we're going to look at the properties of the binomial distribution here. When we're working with a binomial problem, you're going to notice that there are a fixed number of trials that are already predetermined for you. It has to be two or more. So fixed number of trials, that means like, say we're throwing a Frisbee and, we have a dog and it's going to catch the Frisbee, hopefully. In a binomial problem, you would say, okay, I'm only going to throw the Frisbee 5 times. Okay, so you have already decided beforehand how many times you're going to run this experiment. Additionally, with the binomial problems, the trials, each little trial is going to be independent of the previous trial. So, for example, if we're throwing the Frisbee 5 times, if the dog catches the Frisbee on the first throw, that's not going to affect whether he catches it on the next throw. So, those trials are independent of each other. Whenever we're looking at each trial, we're only looking at two possible outcomes for that trial. Either it was a success or it was a failure. Now, how we frame that, so what does a success look like? What does a failure look like? That's going to change for each problem. But we're just saying there's no gray area here. Either the trial was successful or the trial was a failure. So either the dog catches the Frisbee or he doesn't catch the Frisbee. And then we're the probability of success, so the probability of the dog catching the Frisbee, we're going to assume that that's the same in each trial. So maybe the dog has like a 20% chance of catching the Frisbee each time. So, in this scenario, there's a lot of, if you're thinking about the dog throwing the Frisbee for the dog, of course, in real life, there's a lot of variability. Maybe you throw the Frisbee badly, maybe the wind suddenly picks up. We're going to assume that you are in like some kind of fixed environment where the probability of success is going to remain the same for each trial. Now, the whole thing that we're looking for here with a binomial problem is you're trying to figure out what's the probability of a certain number of successes occurring within those predetermined number of trials. All right, so let's say, what's the probability that the dog catches the Frisbee twice in 5 throws? All right, so we're looking at our predetermined number of trials and looking for a particular number of successes. Now, you could also say, like, what's the probability that the dog catches the Frisbee less than 2 times? What's the probability that the dog catches the frisbee more than 3 times? All right, so you can look for it. You can look for those types of probabilities as well. But we're always looking at it in terms of number of successes, not number of failures. Okay, so you can calculate binomial probabilities by hand. The formula is very complicated. So instead, we are going to use the functions that are pre-built into our calculators to calculate binomial probabilities. So let me show you where to find those. All right, so if you'll grab your calculator. Okay, mine's loading. There we go. Let me clear that out. All right, so if you're trying to get to the binomial, the built-in binomial functions in your calculator, you're going to go to second and then vars. Notice vars is kind of like diagonal down from the stat button. All right, so if you go to second and then vars, that's going to take you to the distribution list is what we would call this, the distribution list. Now you got to scroll way down to get to binomial. So scroll way down. There it is. We have two options, binom PDF, binom CDF. Let's talk about what the difference is and when are you going to use each. All right, but before we get into those that information, let me just show you what it looks like when you click on one of these. If you click on one of them, this is a TI-84 that I'm emulating here on the screen. But it'll ask you for three things. It'll ask you for the number of trials. It'll ask you for something called P, and then it'll ask you for an X value. Trials, that's the number of trials like we talked about. P is the probability of success. X is the number of successes that you're looking for. Okay, so let's go back and write all that down. Okay, so when we are accessing the binomial distribution on our calculator, if we're trying to find the probability that X is equal to a number, we're going to use the binom PDF function. All right, so we're looking for the probability that X is equal to a number. So say the probability that the dog catches the frisbee exactly 2 times. Then we're using binom PDF. All right, and then in this notation here, N is the number of trials, is the probability of success, and then X is the number of successes that we're looking for. Okay, so they have to tell you all that in the problem. They have to tell you the number of trials, they have to tell you the probability of success, and they have to tell you the number of successes that you're looking for. All right, so that's for the equal to problems using the binom PDF. If you're looking for the probability that X is less than or equal to a value, so say the probability that the dog catches the frisbee 4 or less times, then we use the binom CDF function. There's no good way to remember that. You just got to remember it. So there's no, I don't have any like cute little saying to remember when do you use P, when do you use C. For the equal to problems, you're doing PDF. For the less than or equal to, you do CDF. Now, there's one additional thing that I've sort of glossed over here that I do want to take a second and talk about. I just threw this in there and I didn't even explain why, but notice that this is a less than or equal to. There's no option for anything else. There's only the option for an equal to problem or a less than or equal to problem. So if you are asked something like find the probability that the dog catches the frisbee less than 3 times, then you have to adjust this because you've got to make it match one of these two formats. All right, so you sometimes will have to make little adjustments so that your probability, so that we can frame it in such a way that our calculator is able to find that probability. So, for example, if the dog catches the frisbee less than 3 times, that's the same thing as saying that he catches it 2 or less times. Right, so we may have to make some small adjustments to our questions to frame the question in such a way that the calculator can handle that. Okay, let's look at an example. All right, so it says a researcher wishes to conduct a study of the color preference of new car buyers. Suppose that 30% of this population prefers the color blue. So they're saying 30% of car buyers prefer to buy a blue car. If 18 buyers are randomly selected, what's the probability that exactly 10 buyers would prefer the color blue? So we've got everything we need right here to calculate this probability. First of all, just so you know, whenever you get to the practice test and to the actual test, it's going to be a lot harder to tell which is which. It's going to be hard to tell, like, is this binomial, or is this Poisson, or is this just a, discrete probability distribution? All right, so, or is this just a general discrete probability distribution, I should say. So let's talk about how I could look at this and immediately tell that it's a binomial. So remember, binomial is fixed number of trials. I'm only looking at 18 new car buyers. That's my number of trials. I'm going to go and ask 18 people what their preference is. Another property of the binomial distribution is that the trials are independent. Okay, that makes sense here. If one person says they prefer a blue car, that's not going to affect what the next person says, right? So each person has their own personal preference. The probability of success is the same in each trial. They told us the probability of success. They say that 30% of the population prefers the color blue. All right, so we've been told the probability of success. We've been told the total number of trials. And then another property of the binomial distribution, there's only 2 options, a success or a failure, right? So you either prefer the color blue or you don't prefer the color blue. There's no in between, right? So there's not like, oh, I sort of prefer it, but I sort of prefer this. No, you either prefer one or the other, right? So it's not there's no gray area in between that. It's a yes or no question. All right, and then we're looking for the number of successes within that predetermined number of trials. And so that's what we're looking for here. We're looking for what's the probability that exactly 10 of our buyers prefer the color blue. Sorry, y'all, somebody's calling me. Okay. So what's the probability that exactly 10 of our buyers prefer the color blue? All right, so we're looking for the so that's how we know that it's binomial. So all of this combined tells me that this is a binomial problem. Okay, so the fixed number of trials, the fact that they told me the probability of success, the fact that there's only 2 options for the preference. You either prefer the color blue or you don't prefer the color blue. And the fact that we're looking for a certain number of successes within those fixed number of trials. Okay. So the word exactly here tells me that I'm looking at an equal to problem. So I know that that's going to be binomial PDF. But I'm looking for the probability that exactly 10 people prefer the color blue for their car. All right, so we're going to do binomial PDF, but we need N, P, and X. So N is our number of trials. That was 18. P is our probability of success. That's 30% or 0.30. All right, so do make sure you change that, 0.30. And then X is our number of successes. Let me just write what those are all equal to. All right, so we're looking at binomial PDF. NPX would be 18, 0.30, 18, 0.30, 10. Now, I like to write this down. You don't have to write it down. But like if you're doing your homework, and or you're doing the practice test or something, I find it helpful to write this down. That way, if I go back and look at it later, I know what I plugged in. So I don't have to go back and read the question again. I know exactly what I plugged in. So I like to write this part down, but it's not required. Okay. So let's grab our calculator and type in. Oh, we just so happen to be on the Binomial PDF screen, but I'll go back through that again. You go to vars, second vars, and you're going to scroll way down. You can also scroll up and get to it a little bit faster. It's not super fast. But Binomial PDF is the one we're doing because it's an equal to problem. We had 18 trials, right? We were going to ask 18 people. Probability of success was 0.30. And yeah, just double checking that 18 was right. And then we were looking for the probability that exactly 10 people preferred the blue car. All right, so now we just hit paste. So hit enter. That's going to paste that onto your screen. All right, so now you can double check, make sure everything looks right. 18.3010, everything looks fine. Hit enter, and there's your probability. We always do 4 decimal places with binomial probabilities. So it's going to be 0.0149. 0.0149. All right, and so if you were to convert that to a percentage, if you're thinking in that, I always like to kind of think about that. This would be about 1.5% or 1.49%. So about if we were to say what's the probability that exactly 10 buyers prefer the color blue, it's about a 1.5% chance that exactly 10 people preferred the color blue. All right. Next, it says a certain insecticide advertises that it kills 65% of all insects in a laboratory experiment or in laboratory experiments. Okay. So a sample of 9 insects are exposed to the insecticide in a particular experiment. What is the probability that exactly 4 insects die? All right. So whoa, back up. Okay. 65, this insecticide kills 65% of all insects. We're looking at a sample of 9 insects that are being exposed to this insecticide. And we're looking for what's the probability that exactly 4 die. Right, so our probability of success is 0.65. Number of trials is 9. Total number of successes that we're looking for is exactly 4. All right, so there's N, P, and X. All right, so N would be 9. X is exactly 4. P is 0.65. All right, this is again, we see the word exactly. That tells me that this is an equal to problem. I'm looking for the probability that X is equal to 4. That tells me that it's a binomial PDF problem. Right, and then the 9, N is 9, P is 0.65, X is 4. Right, so let's grab our calculator. Second bars, go down to binomial PDF. Right, 9 bugs, 65% chance that they die. What's the probability that exactly 4 die? Right, then hit paste and enter. And there we go, 0.1181. That would be about 11.81%, about 12% chance that exactly 4 bugs die. About a 12% chance that exactly 4 of those insects died. Rest in peace. Okay, so again, you can, if you want to do this on your own, I think this would be a great exercise to think about, how do I know that this is binomial? So think about, do I have a fixed number of trials? Do I know the probability of success? Are the trials independent? So in this case, that would be like, if one bug dies, is that going to affect whether another bug dies? And then lastly, we're thinking like, are we looking for a certain number of successes within that predetermined number of trials? So, and then also think about, is it like a success or a failure situation? So either the bug dies or it didn't die. Okay, so think of it would be a really good, I think it would be a really good exercise for you to write all that out. I think it would really be helpful, like whenever you get to the exam time. All right, this one, in my opinion, slightly increases in difficulty. Just some of the wording makes it a little bit more complicated. Okay, so the scenario here, it says you have a quality control inspector and they're looking at light bulbs off of a production lot. All right, so they drew a sample of 16 light bulbs from a production lot. All right, and so here's a little bit of background information for you. It says if the number of defective light bulbs is one or less, then the lot's going to pass inspection. Okay, so if they draw those 16, they pick 16 light bulbs off of the production line. If there's only one or less, what that would be zero, one or zero defective light bulbs, then they're going to say, okay, that lot passes inspection. Go ahead and send those out. All right, and then it tells us that suppose that there's in reality 20% of these bulbs are defective. What's the probability that the lot actually passes inspection? All right, so we've got a lot of information here. The number of defective light bulbs is one or less, then we're going to pass inspection. In reality, 20% of bulbs are defective. Now, here's the wording here that I find a little bit complicated. What's the probability that it passes inspection? All right, so we've got to reframe this and think, okay, what does passes inspection mean? All right, so if it passes inspection, then we know that the number of defective light bulbs must have been one or less. All right, one or less. All right, so that's the probability that X is less than or equal to 1. All right, so you could reframe that and say, okay, the probability that it passes inspection is the probability that the number of defective light bulbs is 1 or less. Okay, so let's think about this. We've got a fixed number of trials. We're looking at exactly 16 light bulbs, right? We took 16 light bulbs off of the production line. That's our number of trials. We're going to test each one. The probability of success. We're looking at success here is that the bulb is defective. I know that is kind of confusing because you're thinking, wouldn't that be a failure? Yes, that would be a failure of the light bulb. But in this experiment, a success is that we find a defective light bulb. All right, so 20% chance that the light bulbs are defective. So that's our probability of success, 0.20. And then we're looking for the probability that we observe one or less successes, right? And then also this another reason we know this is binomial is because there's only two outcomes of this experiment, right? Either the light bulb works or it doesn't work. Okay, so this time we're looking at a less than or equal to problem. That means it's not binom PDF this time, it's binom CDF. All right, so still N, P, and X. Number of trials is 16. We're looking at those 16 light bulbs. 20% of them are defective, and we're looking for the probability that X is 1 or less. All right, so the CDF is going to tell it, okay, look at the probability that it's this number or less. All right, so that's built into the calculator. Now, another thing that you could do, I was just thinking about this. If you like only wanted to use the binom PDF function, you could say, okay, well, this is the same thing as saying, I'm going to do binom PDF of 16 0.201 and then plus binom PDF 16.20 and 0. So you could manually calculate each one of those and then add them together. It would just take you forever. All right, so you could only use the PDF function, but the whole point of doing this is that we're trying to make this as easy as possible on ourselves. So using the CDF function makes this a whole lot easier than doing those each individually. All right, so let me clear that out. Let's go to second vars, scroll way down. Oop, there we go, binom CDF. Trials, let's see, I've already forgotten. There we go, 16 bulbs, 0.20. All right, so 16 bulbs, 20% chance that they're defective, and then we're looking for the probability that X is 1 or less. All right, so CDF 16.201, everything looks good. Hit enter, and there's our probability, 0.1407. So that's about a 14% chance that the lot passes inspection. 0.1407, or about 14% chance that the lot passes inspection. Right, and then here's our last problem. Again, just slightly increasing in difficulty here. It says a real estate agent has 13 properties that she shows. All right, that's our number of trials. She's, looking at, she's going to sell, or she's going to show 13 houses this week. She feels that there's a 25% chance of selling any one property during a week. All right, so she's got a 25% chance of selling the house that she shows. Find the probability of selling less than 4 properties in 1 week. All right, so less than 4. All right, so we're looking at the probability that X is less than 4. But remember, we only have these two options. We only have the equal to option or the less than or equal to option. So let's think about this. She's showing 13 houses. That's the maximum. She can only sell up to 13 houses. She can't sell 14. She doesn't have 14 properties. So the maximum number of houses that she could sell in a week is 13. The minimum is 0. I forgot to include that one, but it is possible that, maybe she's sick. Maybe she doesn't do anything that week. And she sells 0 houses. All right. So if we're saying the probability that she sells less than 4, that's all these folks. And also this one. All right, so less than 4 is the same thing as saying 3 or less. Right, so less than 4 is the same thing as saying 3 or less. All right, so let's set up our binomial problem. We're doing CDF this time because it's a less than or equal to problem. We've got 13 trials, right? 13 opportunities to sell a house. 25% chance of selling a house, so 0.25 for our probability of success. And then number of successes that we're looking for is 3 or less. All right, so the CDF tells it, okay, do this number or less. All right, so let's plug this in. Clear that out. Second bars go way down. The binomial CDF, 13 houses, 25% chance of selling a house. We're looking at 3 or less, right? Yes. All right, so then go down to paste, hit enter, run it, and there we go. 0.5843. 0.5843. 0.5843. So we're saying there's about a 58% chance, 58.43% chance that she sells less than 4 properties that week. Okay, that was everything for this section. There are some slightly more complicated problems, or there may be some slightly more complicated problems. I'm going to go through and make little short clips to help you with those problems, just so that you don't have to watch this whole video several times. You can just look at those little clips. All right, so I will see you guys in the next video. I hope y'all have a great day.